Hello, my name is Aarya Baldota and I'm from Texas Christian University. For this summer's OREU program, I studied image analysis and quantitative metallography for improving properties of cold spray tantalum. I would like to thank my mentors, Dr. Brady Butler from DevCom ARL, Texas A&M University, Department of Materials Science and Engineering, Griffin Turner, Texas A&M University, Department of Materials Science and Engineering. I would like to thank my sponsors, Online REU program at Texas A&M University, DevCom ARL. I would also like to thank my peer, Robert Kaman from Iowa State University. Tantalum as a transition element possesses good resistant properties for corrosion, chemical, as well as heat. We see in this graph that tantalum has one of the highest melting points among most other elements and is called a refractory metal. While most metals in the group that tantalum belongs to are used in industrial applications like alloy constituents, tantalum has found application in both alloy as well as its pure form. Tantalum as a metal has important properties that make it a suitable metal, specifically for the high pressure cold spray process. Tantalum is quite expensive and thus cold spray is a perfect method as it uses less material. Tantalum is widely used to cold spray steel. Steel is widely used in multiple manufacturing industries. It's used in aircraft engines, electrical devices, surgical implants, nuclear power plants, and missiles. Research, tantalum is sprayed on a stainless steel substrate using the high pressure cold spray method. Cold spray enables the tantalum powder to be sprayed on the steel substrate without melting. The particles of the powder are sprayed on the substrate using a gun with a nozzle which has very high speeds, which results in a good bonding between the coating and the substrate. The low temperature and solid state deposition associated with cold spray allows refractory materials such as tantalum to be deposited without high temperature requirements. The main aim of this method is to obtain a dense and non-porous coating. This process increases the hardness and adhesion strength of the material. Tantalum is chosen to work with high pressure cold spray process to develop thin coating and layers on the steel substrate to obtain a wear and corrosion resistant material. When the tantalum is cold sprayed, there are pores formed in the coating which can cause issues in the life of the material, and these are the pores that will be examined further to determine how they affect the sprayed material. For further understanding of these pores, I used the ImageJ software and applied them to multiple images of the same sample. I first set a scale and made it global so that every image would be analyzed under the same scale. I then applied the Kuwahara filter, which made the pores more definite and less blur. I then applied the threshold, which makes only the pores visible against a neutral background and gets rid of unnecessary objects in the image. Then I chose the set of measurements that I wanted of the pores, such as area, circularity, position, etc. I then ran the Analyze Particles function to get results of each and every pore and its measurements. This caused all the pores to be labeled and each of them had their own set of measurements. As we can see in this table, the x is the coordinate in the horizontal direction from left to right. Y is the coordinate in the vertical direction of the pore. Circularity determines how round the pore is. Min-ferrite determines the thickness of the coating, and so on. The x global coordinate is the position of the pore with respect to a single coordinate system, adding the field of views of the other images. For this sample, the percent porosity was 0.15175 micron. Two samples of tantalum powders were tested from two different companies. Two different codes were used in Python to see the differences in the two samples. As we can see in the scatter plot, powder G has more pores compared to powder S. The scatter plots are of the pores distributed in the x direction with respect to the y direction. The histogram shows that the distribution of pores in powder G sample is more even as compared to the powder S sample. Further differences noticed in the two samples which will be further explored to determine which of the powders is better suited for the high pressure cold spray on a steel substrate. Some of the experimental results that were run in the lab so as to compare with the image analysis are the following. A Vickers hardness test was run on the two samples. A micro indentation was made on the image. The indentation in this case is made out of a diamond. Mostly the shape is symmetrical depending on the material. Sometimes it can skew, causing one of the lengths to be longer than the other. The lengths are measured from point to point both ways. Using the Vickers hardness calculator, an average of the two lengths is calculated, called the Vickers hardness value. These values don't have any unit as such. Hardness is resistance to plastic deformation. If the hardness value is higher, that means that particular spot did not deform as much. On the other hand, if it is a lower value, then that spot was more deformed than the others. Pores affect the hardness values significantly. The pores table indicates if the indentation hit a pore or not. The powder G sample has lesser spots with no pores as compared to the S sample, as we can see in the table. The value for the average hardness value for the G sample is 262.56, while for the S sample is 257.8, which means that powder G sample has more hardness. As we can see in the image, the indentation is a diamond. The big black spot is actually the tungsten chromium carbide alloy, which is added knowingly to the coating material and is said to improve the hardness of the coating. I attempted to graph the hardness values and the thickness of the area of interest of the sample with respect to the global position of the images. And although it is not a clear-cut correlation, I did notice a similar trend in the two values. On the edges of the sample, where the coating is thicker, the hardness value is higher as compared to the mid portion, which is not as thickly cold sprayed. In conclusion, we see that from the two samples that were tested in the lab, powder G is proven to have better hardness than powder S, but we do not know why. Hardness and thickness have a correlation which is somewhat directly proportional. If we can relate thickness of the coating with the pores created in the region, then we can correlate the porosity with the hardness. We can attempt to do this by making a function which is a combination of thickness and porosity and then relate it to the hardness values. These were the works that I cited. I would like to take this opportunity to thank everyone once again at Texas A&M University, the ORU program, my mentors Dr. Brady Butler and Griffin Turner for this learning experience. Thank you.